Hello, this is the Chapter 4 review. I'm going to review some story problems, so this is more of the justification and problem solving type problems that you will see on your summative assessment. So I'll just jump right into it. I have two examples, one arithmetic and one geometric. So we're going to start off with the geometric one. So in this problem, it says Joey's starting salary at his job was $30,000. He gets a 3% raise every year. And his salary listed below is what he has after 2 years. So there's his first amount right here, which we're going to call G1. Now this is after 1 year, he makes $30,900, and then he got his raise again. So after 2 full years of working there, he has $31,827. So what we could do, since this is a geometric sequence, is to find the common ratio. I'm going to take the second number divided by the first number. So I'm going to take 30,900 and divide it by 30,000. And try doing this along in your calculator too. That's going to give me 1.03. So if I took my second divided by the first number, that means that my common ratio is 1.03. And then I'm also, while I'm at it, just going to identify that my first term, G1, is 30,000. So with this information, I can use the explicit formula for a geometric sequence, and we can calculate how much he will make after 8 years of working. So there's a couple of important things to note in this problem. First of all, it's geometric, so it's going to be growing exponentially, which is the type of function that it is. So it's going to be modeled by the explicit formula, G sub n equals G1 times r, because you're multiplying by the common ratio, to the n minus 1 power. And again, the n minus 1 is not being multiplied by r. This is in the exponent spot because it is an exponential function. So now what we have to do is kind of analyze what term number we're solving for, because it is after 8 years of working, but that doesn't necessarily mean that it's the 8th term. So if we go back to this very beginning thing, he makes $30,000 his first year. So after 1 year, he is at his second term in the sequence, and after 2 years he's at his third term. So after 8 years of working, that would technically be his 9th term. And what I'm going to do is substitute the information from R and G1 into my formula here. So G1 was 30,000 times 1.03 to the n minus 1 power, so 9 minus 1. So what I'm going to do is demonstrate in the calculator here how you would push this, or put it into your calculator actually. Because what I've seen the mistakes people have made are they're multiplying 1.03 to the times the exponent. But again, it's 1.03 to the power of that number. So the power button to get up to the exponent is right above the division key on this type of calculator. And it's 9 minus 1, so I'm taking 1.03 to the 8th power, and it gives me this value. Now that covers this part right here. Now I just need to times it by 30,000 and hit enter. So there's his salary, $38,003. And I'll throw just the 10 cents on there. In context of the problem, it makes sense that we can round to 2 decimal spots, because that would be how many cents exactly the dollar amount is to. But again, in terms of an actual sequence, you would want to give the whole number. So I'm going to be pretty lenient here in terms of the problem and just say we can have it as $38,003.10. So in context of the problem, let's go that last step then and answer this in a complete sentence. You can say after 8 years, Joey will make $38,003.10. And I'll throw a little dollar sign in front of there, and that would be it for that problem. So this next example is going to be an arithmetic sequence problem. So in this problem, a truck driver is carrying 3,500 pounds of cargo and is dropping off 300 pounds at every truck stop. So what we are going to do is use a formula to calculate how many pounds of cargo he's going to have after 8 stops. So what I do is give you the first couple numbers that he has here. This would be called A1. Now that it's arithmetic, we're going to use A's instead of G's. So after 1 stop, he loses 300 pounds. So after 1 stop, that is his second term. And after 2 stops, he has 2,900 pounds, and that's his third term. So If you want, what you can do is pause this video, work ahead a little bit, and see if you can calculate how much he will have after 8 stops, or just keep watching the video. So, very insanely similar to the last problem. Our first term here is not technically the first stop. Just like in the last problem with the number of years was 1 less than the term number. So 8 stops is 1 less than the term number in this case, again, because he has 3,200 pounds after 1 stop. So his second term is after 1 stop, and his third term is after 2 stops. So it would be his 9th term after 8 stops. So we are actually going to be calculating AN, blah, blah, blah. We're calculating A9. And let's get the formula. So the formula will be arithmetic. AN equals A1 plus the common difference D times N minus 1. So let's quickly identify what A1 and the common difference D are. A1 is the first term. So first term here is 3,500. He is starting with 3,500 pounds of cargo. And since he is dropping off 300 pounds, he's losing cargo, you can take the second number minus the first number, and you'll get negative 300. So what I'm going to do is write my explicit formula. A sub n equals 3,500 plus negative 300 times n minus 1. And we are going to calculate the 9th term. So in order to calculate the 9th term, we're just going to substitute the value of 9 in for n. So I have 3,500 plus negative 300 and then 9 minus 1. So that's 3,500 plus negative 300. 9 minus 1 is 8. So order of operations tells you should probably do this part next. By probably, I mean you should, because this is multiplication, and then you would add. So you have 3,500 plus negative 2,400. So at the very end you have 3,500 plus negative 2,400, and that is 1,100 pounds. So if I were to answer this in a complete sentence, which since it is going to be a problem-solving problem, you will have to do that. In context of the problem, you can say the driver will have, will have 1,100 pounds of cargo after 8 stops. Okay, so that is your final answer. Again, in context of the problem, please do not just leave your answers 1,100 pounds. Go that extra mile and just say that that's how much he has after the 8 stops. And then the last ones that I have. I'm going to do 2 of these, so we're going to create a table and graph to model each of these sequences. Again, I have 1 arithmetic and 1 geometric. And the point of doing this is to really nail down that relationship that arithmetic sequences are linear and geometric sequences are exponential. So what I'm going to do is start filling in this table of values, and we will keep the sequence going until we have 8 terms so that I can fill in the table. So I'll just fill in these first 4 terms. I have negative 8, negative 5, negative 2, and 1. And if we can catch our pattern, like I said, this is arithmetic. We're going to take the second number minus the first number. Negative 5 minus negative 8 is positive 3, which means that I have a common difference of positive 3. So my sequence is increasing as we add the numbers. We're going to add the common difference to the next term. So I'm going to take 1 plus the common difference to get my next term. So 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 3 is 10. And 10 plus 3 is 13. So that would be my next 4 values in the sequence. Dog is barking. Okay, Charlie! Okay. Now I'm going to plot these points. So 1 at negative 8, 1, 2, or actually, you know what? I can probably count by 2s. Since 13 is going to be off my graph, I will actually count by 2s. So I'm going to call this negative 2, negative 4, negative 6, negative 8, okay, and so on. So I'm going to count my y-axis by 2s, and I will count my x-axis by 1s. So these are just going to go 1 at a time. So my first point, if I'm counting by 2s, would be 2, 4, 6, 8 down here. 2 is at negative 5, so that would be 2, 4, and right in the middle here. And then I have 3 at negative 2, 4 is at 1, 5 is at 4, 6 is at 7, so 2, 4, 6, 7 is up here. 7 is at 10, so 2, 4, 6, 8, 10. And then the last point is 8, 13. So over here at 8 on the x-axis, I'm up 2, 4, 6, 8, 10, 12, 13. And this again is a discrete relationship, just to bring in the concept of discrete versus continuous, since you cannot have a 1.5 term or a 5.2 term or anything. You can only have integer terms, 1, 2, 3, 4, 5, and so on. So it is a discrete function. If it were continuous, you would be able to have like the 4.6 term number or something, but we can't calculate that. It wouldn't make sense in terms of the problem. Sequences go one term at a time, so that's why the graph is discrete. And again, just to tie down this concept, it is linear because it is increasing by a constant rate. So key terms that I'm going to be looking for. I'm looking for people to say and use the word constant as far as an increase or decrease. I would like you to say this is the common difference, which is why it's arithmetic, which means you are increasing by that same amount every time. And then, let me see if there's anything else, any other goodies. It is linear. Tie that down, that is a linear function because the sequence is arithmetic. Okay, so it's a bunch of key terms I'm going to use here. So on the next example, I'll just do a little compare-contrast at the very end actually, but on the next example, it's going to be very similar to this, except we're not going to have these same 4 terms. They're all going to be different because we're going to be dealing with geometric sequences. So on this next graph, this one is geometric, so I'll write that at the top. In order to figure out the common ratio, we would take second divided by first. So if you take 1.5 divided by 0.5, you're going to get 3, which means that our common ratio R is 3. So you're multiplying by 3 every time. So in your calculator, you can work out the other values. So 0.5 is my first term, then 1.5, 4.5, 13.5. And then you just keep multiplying. I get 40.5, 121.5, 364.5. Wow, this is growing insanely fast. By insanely fast, I can use the word exponential, because exponential means it's going to be growing faster and faster because you are multiplying by a constant number every time. So in this case, we are multiplying by 3 every time. So the function is growing insanely fast. So what I'm going to do actually on my y-axis, since these numbers are counting insanely fast, I'm going to count by hundreds on the y-axis, which is going to really require us to eyeball these x values really close. So in this first one, if you think about it, from 0 to 100, we're only going up 0.5. So this first term is so insanely close to the x-axis, and the terms are going to be like that until we pass 100, which that's not going to be until our 6th term. So my second term is at 1.5, so these numbers are going to slowly increase until you get to your 5th term is close to half, because 40 is almost at 50, and then I get to my x value of 6, which brings me a little bit above 100 at 120. My 7th value is at 364, so that's going to be up here somewhere. And then my last value, my 8th term, is all the way above 1,000. So this graph, there's 400, 500, 600, 700, 800, 900. 1,000 is all the way up here. So this last value is technically going to be just a little bit off the graph. And again, it's going to have this curvy shape when it's a geometric sequence because it is exponential. So again, the key terms that I'm looking for here, this is exponential, or you can say it is an exponential function. We are multiplying by the common ratio, and that's how you got your other terms, is we multiplied by that common ratio, which was R. And then let me just backtrack real quick. Was there anything else that we had? Oh yeah, and this was a geometric function, or a geometric sequence, so that's what's all the way at the top. So if we do a little quick compare and contrast, if you look at all of the y values on the left-hand side here, all these y values are multiplying by 3 every time, and that's what creates this big spike in the graph. Notice how fast it grows over such a short amount of time. I mean, it really skipped up like 1,000 units just between these couple values. So exponential is going to have that huge jump increase. Versus if I backtrack to the linear function, notice that it is a straight line. All, I repeat, all arithmetic sequences have this linear looking graph, this linear function. the linear discrete function. And again, it's discrete because you can't have these terms in the middle of these two numbers. I don't have a 5.5 term. So again, little compare and contrast between these two values, or the two different types of functions here. And then if you have to go back in the video, rewatch any of the story problems, I really encourage that you look at the relationship from these previous problems between your term number and the number of years in the problem.